Nenomatica, where mathematics meets YouTube excellence. Welcome to this math tutorial. Today, we'll learn about an important property of radicals known as the fourth law of radicals, which deals with dividing radical expressions. Let's begin with the theorem. If we have the root of a divided by b, and both a and b are defined with b not equal to 0, then the root of a over b equals the root of a divided by the root of b. Now, let's see the proof of this theorem. We start by understanding what the nth root means. If we have the nth root of a over b, we can rewrite this using fractional exponents. So the nth root of a over b equals the fraction a over b raised to the power of 1 over n. Next, using the property of exponents for fractions, we can write this as a raised to the power of 1 over n divided by b raised to the power of 1 over n. Finally, we recognize that a to the power of 1 over n is the nth root of a, and b to the power of 1 over n is the nth root of b. So our result is the nth root of a divided by the nth root of b. Now let's solve some exercises to practice applying this property. First exercise, find the value of the square root of 0.04. To solve this, we'll first convert the decimal to a fraction. 0.04 equals 4 divided by 100. Using our radical division property, the square root of 4 over 100 equals the square root of 4 divided by the square root of 100. The square root of 4 is 2, and the square root of 100 is 10. So our answer is 2 divided by 10, which simplifies to 1 over 5, or 0.2. Let's try another exercise. Find the value of the square root of 1 over a squared. We can apply our division property for radicals directly. The square root of 1 over a squared equals the square root of 1 divided by the square root of a squared. The square root of 1 is simply 1, and the square root of a squared is a. So our final answer is 1 divided by a, or 1 over a. For our final exercise, we need to simplify the square root of 25 over 9. To simplify this expression, we'll use a fundamental property of square roots. When we have a square root of a fraction, we can rewrite it as a fraction of square roots. Specifically, the square root of a over b equals the square root of a divided by the square root of b. Let's apply this rule to our first example. We can rewrite the square root of 25 over 9 as the square root of 25 divided by the square root of 9. Now, we can simplify both the numerator and the denominator. The square root of 25 equals 5, and the square root of 9 equals 3. Let's move to our second example. We need to simplify the square root of 20 over 5. Again, we'll use our rule to rewrite this as the square root of 20 divided by the square root of 5. We can simplify the numerator further. 20 can be written as 4 times 5. So the square root of 20 equals the square root of 4 times 5, which equals the square root of 4 times the square root of 5. The square root of 4 is 2, so we get 2 times the square root of 5, divided by the square root of 5. Now, we can cancel out the square root of 5 in the numerator and denominator, giving us a final answer of 2. Let's move to our third example. We need to simplify the expression, the square root of 3 times the square root of 6, all divided by the square root of 2. First, let's simplify the numerator. When we multiply square roots, we can multiply what's inside the square roots. So the square root of 3 times the square root of 6 equals the square root of 3 times 6, which is the square root of 18. Now, let's use the rule for the square root of a fraction again, but in reverse. We can rewrite this as the square root of 18 divided by 2. We can simplify the fraction inside the square root. 18 divided by 2 equals 9. And the square root of 9 equals 3. So our final answer is 3. Welcome to this math tutorial on simplifying radical expressions. Today, we'll learn how to work with radical expressions and solve some example problems step by step. Before we start solving problems, let's review some important properties of radicals that we'll be using. First, the product rule for radicals states that the square root of a times b equals the square root of a times the square root of b. Second, the quotient rule for radicals tells us that the square root of a divided by b equals the square root of a divided by the square root of b. Third, we can simplify radicals by finding perfect square factors. For example, the square root of 12 can be rewritten as the square root of 4 times 3, which equals 2 times the square root of 3. Now, let's work through our first example problem. we need to calculate the value of the expression, the square root of 15 times the square root of 50 times the square root of 3, all divided by the square root of 6 times the square root of 30 times the square root of 2. Let's solve this step by step following our algorithm. The first step is to apply the product rule of radicals to combine the terms in the numerator and denominator. In the numerator, we multiply what's under the radicals. 15 times 50 times 3 equals 2,250. In the denominator, we multiply. 6 times 30 times 2 equals 360. Now, let's apply the quotient rule for radicals to simplify the fraction. Using the quotient rule, we can rewrite this as the square root of 2,250 divided by 360. Next, we'll simplify the fraction inside the square root. Let's divide both the numerator and denominator by their greatest common divisor. 2250 divided by 360 equals 25 divided by 4, or 6.25. Now, we need to convert our result to simplest radical form. We can express 25 fourths as 6.25, but the standard form for our answer should be in the form. We can express 25 fourths as 6.25, but the standard form for our answer should be in the form of a fraction with a radical. So, the square root of 25 fourths equals the square root of 25 divided by the square root of 4, which equals 5 halves. Let's move on to our second example. We need to simplify the expression, the cube root of 32 divided by the cube root of 2. For this example, we'll apply the quotient rule for cube roots. Using the quotient rule, we can rewrite this as the cube root of 32 divided by 2. Next, we'll simplify the fraction inside the cube root. 32 divided by 2 equals 16. Now we need to find the cube root of 16. We know that 16 equals 2 to the power of 4. For a cube root, we can rewrite this as 2 to the power of 4/3. Using the power rule, this equals 2 to the power of 1 and 1/3, which is 2 times the cube root of 2. Let's solve one more example, power of 4/3. Using the power rule, this equals 2 to the power of 1 and 1/3, which is 2 times the cube root of 2. Let's solve one more example. We need to simplify the expression, the square root of 16 divided by 125. For this example, we'll apply the quotient rule for square roots. Using the quotient rule, we can rewrite this as the square root of 16 divided by the square root of 125. Next, let's simplify the radicals in both numerator and denominator. For the numerator, we know that the square root of 16 is 4. For the denominator, we can write 125 as 5 cubed, so the square root of 125 is 5 times the square root of 5. Now, let's rationalize the denominator by multiplying both numerator and denominator by the square root of 5. This gives us 4 times the square root of 5 in the numerator, and 5 times 5, which is 25 in the denominator. Let's summarize both numerator and denominator by the square root of 5. This gives us 4 times the square root of 5 in the numerator, and 5 times 5, which is 25 in the denominator. Let's summarize what we've learned about simplifying radical expressions. We've covered several key rules and steps for simplifying radicals. First, the product rule allows us to break up or combine the products of radicals. Second, the quotient rule helps us rewrite fractions involving radicals. Third, we can simplify expressions by finding perfect square or perfect cube factors. Finally, we sometimes need to rationalize denominators by multiplying both the numerator and denominator by the same radical. By following these steps systematically, you can simplify any radical expression. Thank you for watching this tutorial on simplifying radical expressions. With practice, let's take a look at the examples we're going to solve. Let's start with our first example. We need to simplify the fifth root of 32 divided by 243. For this problem, we can use a key property of radicals. The fifth root of a fraction equals the fifth root of the numerator divided by the fifth root of the denominator. So the fifth root of 32 over 243 equals the fifth root of 32 divided by the fifth root of 243. Now, let's identify what 32 and 243 are in terms of powers. 32 is 2 to the fifth power, and 243 is 3 to the fifth power. When we have the nth root of a number raised to the nth power, the result simplifies to just the base. So the fifth root of 2 to the fifth equals 2, and the fifth root of 3 to the fifth equals 3. So our final answer is 2/3. Now, let's move on to our second example. We need to simplify the fourth root of 5 to the fourth power divided by 2 to the 12th power. For this problem, we'll use another key property. When we have a radical with an exponent inside that matches the root index, we can simplify by writing it as a power. Let's start by rewriting this expression. We have the fourth root of 5 to the fourth power divided by 2 to the 12th power. We can rewrite 2 to the 12th as 2 to the third, all raised to the fourth power. This gives us 2 to the third equals 8. So we have 8 to the fourth power in the denominator. Now we have the fourth root of 5 to the fourth divided by 8 to the fourth. This can be rewritten as the fourth root of the fraction 5 to the fourth over 8 to the fourth. When we have the fourth root of a fraction raised to the fourth power, it's simply equal to that fraction. So the fourth root of 5 over 8, all to the fourth power, is just 5/8. Let's continue with our third example. We need to simplify the cube root of 2 divided by the cube root of 16. For this problem, we'll use the property that allows us to combine radicals with the same index under one radical. We can rewrite the expression as the cube root of 2 divided by 16. Simplifying the fraction inside the radical, we get 2 over 16, which is 1/8. Now we can rewrite 1/8 as 1/2 cubed. When we have the cube root of something raised to the cube power, it simplifies to just the base. So the cube root of 1/2 cubed is just 1/2. Let's finish with our fourth example. We need to simplify the cube root of 108 divided by the cube root of 4. For this problem, we'll use the same property as before to combine the radicals and then factor inside the radical to simplify. We can rewrite the expression as the cube root of 108 divided by 4. Let's factor 108. We can express 108 as 4 times 27. Now, we have the cube root of 4 times 27 divided by 4, which simplifies to the cube root of 27. 27 equals 3 cubed. So the cube root of 3 cubed is simply 3. Therefore, the final answer is 3. Today we'll verify these two equalities from the exercise. The square root of 40 divided by the square root of 2/5 equals 10, and the seventh root of 4 divided by the seventh root of 4 times 10 to the 7th power equals 1/10. Let's start with our first problem. We need to verify that the square root of 40 divided by the square root of 2/5 equals 10. First, we'll apply the square root quotient rule, which states that the square root of a fraction equals the square root of the numerator divided by the square root of the denominator. So, the square root of 2/5 equals the square root of 2 divided by the square root of 5. Now, we can rewrite our expression with this substitution. Next, we simplify by multiplying both the numerator and denominator by the square root of 5. This gives us the square root of 40 times the square root of 5, divided by the square root of 2. Using the multiplication property of square roots, where the square root of a times b equals the square root of a times the square root of b, we get the square root of 40 times 5, divided by the square root of 2. Calculating 40 times 5, we get 200. So our expression becomes the square root of 200 divided by the square root of 2. Now we can factorize 200 as 2 times 100, which gives us the square root of 2 times the square root of 100 divided by the square root of 2. The square root of 2 in the numerator and denominator cancel out, leaving us with just the square root of 100. And since the square root of 100 is 10, our final answer is 10. So we verified that the square root of 40 divided by the square root of 2/5 equals 10. Now, let's move on to the second problem. We need to verify that the seventh root of 4 divided by the seventh root of 4 times 10 to the 7th power equals 1/10. Similar to the previous problem, we'll use the quotient property of nth roots. The nth root of a quotient equals the nth root of the numerator divided by the nth root of the denominator. First, let's express our fraction as a single seventh root using this property in reverse. Next, we simplify the expression inside the seventh root. For divided by 4 times 10 to the 7th power equals 1 over 10 to the 7th power. Now, we know that 1 over 10 to the 7th power can be written as 1/10 raised to the 7th power. Finally, by the property of nth roots, the 7th root of 1/10 to the 7th power equals 1/10. So we've verified that the 7th root of 4 divided by the 7th root of 4 times 10 to the 7th power equals 1/10. Thinking face, here's a quick challenge for you. Before we continue, try to solve this similar problem on your own. Simplify. The square root of 50 divided by the square root of 5 halves. Pause the video and try to solve it. I'll give you a hint. Use the same approach we just learned. Pause button ready? Let's solve it together. Using the same approach, we have the square root of 50 divided by the square root of 5 halves equals the square root of 50 divided by the square root of 5 over the square root of 2. Simplifying, we get the square root of 50 times the square root of 2 over the square root of 5. Using the multiplication property of square roots, this equals the square root of 50 times 2 divided by the square root of 5, which is the square root of 100 divided by the square root of 5. Since the square root of 100 is 10, our answer is 10 over the square root of 5. Rationalizing the denominator by multiplying both numerator and denominator by the square root of 5, we get 10 times the square root of 5 over 5, which simplifies to 10 times the square root of 5 divided by 5, or 2 times the square root of 5. So the answer is 2 times the square root of 5. Let's start with our first problem. We need to prove that the quotient of a fifth root of a squared plus 1 to the power of 70 divided by the fifth root of a squared plus 1 to the power of 20 equals a squared plus 1 to the power of 10. Our first step is to use the quotient property of roots. This rule states that the quotient of nth roots equals the nth root of the quotient. So we can rewrite our expression as a single fifth root of the quotient of the expressions inside the roots. Now we'll use another rule, the quotient of powers with the same base. This rule states that x to the power of m divided by x to the power of n equals x to the power of m minus n. So inside our fifth root, we can simplify the quotient by subtracting the exponents, giving us a squared plus 1 to the power of 70 minus 20, which equals 50. Next, we'll use the power of a power rule. This rule states that x to the power of m, all raised to the power of n, equals x to the power of m times n. We can rewrite 50 as 10 times 5. So we have the fifth root of a squared plus 1 to the power of 10, all raised to the power of 5. Finally, we'll use the rule for the nth root of an nth power. This rule states that the nth root of x to the power of n equals x. In our case, we have the fifth root of something raised to the power of 5. So these operations cancel each other out, leaving us with a squared plus 1 to the power of 10. So we've proven that the expression equals a squared plus 1 to the power of 10. Let's review the steps. First, we combined the quotient of fifth roots into a single root. Then, we subtracted the exponents inside the root. Next, we expressed the exponent as a product. Finally, we simplified the root and power to get our answer. Let's move on to our second problem. We need to prove that the product of two cube roots of x squared plus 4 all to the power of 2 divided by the cube root of x squared plus 4 to the power of 7 equals 1 over x squared plus 4. First, we'll use the product property of roots. This rule states that the product of nth roots equals the nth root of the product. So we can combine the product of cube roots in the numerator as a single cube root of the product of what's inside. Now, we'll use the quotient property of roots again. As we saw earlier, this property allows us to combine the quotient of cube roots into a single cube root of the quotient. So we can rewrite our expression as a cube root of x squared plus 4 to the power of 4, divided by x squared plus 4 to the power of 7. Next, we'll use the quotient of powers with the same base again. As we saw earlier, when dividing powers with the same base, we subtract the exponents. In our case, we have x squared plus 4 to the power of 4, divided by x squared plus 4 to the power of 7. This gives us x squared plus 4 to the power of 4 minus 7, which equals x squared plus 4 to the power of negative 3. Now, we'll use the negative exponent rule. This rule states that x to the power of negative n equals 1 over x to the power of n. So we can rewrite x squared plus 4 to the power of negative 3 as 1 over x squared plus 4 to the power of 3. Finally, we'll use the rule for the nth root of an nth power again. Recall that the nth root of x to the power of n equals x. In our case, we have the cube root of 1 over x squared plus 4 to the power of 3. The cube root and the power of 3 cancel out, leaving us with 1 over x squared plus 4. So we've proven that the expression equals 1 over x squared plus 4. Let's review the steps. First, we combine the product of cube roots in the numerator. Then, we combine the quotient of cube roots into a single root. Next, we subtracted the exponents inside the root. Then, We rewrote the negative exponent with a positive 1. Finally, we simplified the root and power to get our answer. Let's look at our problem. We need to simplify this expression. The 9th root of x squared y cubed times the 9th root of x y to the 12th divided by the 9th root of x y to the 21st times the 9th root of x to the 20th y cubed. And we need to verify that this equals 1 over x squared y. Let's begin by combining all 9th roots into a single expression. We can use the property of roots that says, when multiplying expressions with the same root index, we can combine them under a single root symbol. This means we can rewrite our problem as the 9th root of the fraction with numerator x squared y cubed times x y to the 12th and denominator x y to the 21st times x to the 20th y cubed. Now, we need to multiply expressions with same bases in both numerator and denominator. When multiplying expressions with the same base, we add the exponents. In the numerator, we have x squared times x to the 1, which gives us x to the 3. We also have y cubed times y to the 12th, which gives us y to the 15th. In the denominator, we have x to the 1 times x to the 20th, giving us x to the 21st, and y to the 21st times y cubed, which gives us y to the 24th. Next, we'll use the quotient rule for exponents. When dividing expressions with the same base, we subtract the exponents. For x, we have x cubed divided by x to the 21st, giving us x to the power of 3 minus 21, which is x to the negative 18th. For y, we have y to the 15th divided by y to the 24th, which gives us y to the power of 15 minus 24, or y to the negative 9th. Now, we have negative exponents. When an expression has a negative exponent, we can rewrite it as 1 divided by the expression with the positive exponent. So, x to the negative 18th becomes 1 over x to the 18th, and y to the negative 9th becomes 1 over y to the 9th. This gives us the 9th root of 1 over x to the 18th times y to the 9th. Now, let's recognize a pattern. We're taking the 9th root of a fraction. The denominator is x to the 18th times y to the 9th. We can rewrite this as the 9th root of 1 over x squared y to the 1st, all raised to the 9th power. This is because x to the 18th is equivalent to x squared raised to the 9th power, since 2 times 9 equals 18. Similarly, y to the 9th is equivalent to y to the 1st raised to the 9th power. Finally, we use the property that the nth root of a value raised to the nth power gives us the original value. So, the 9th root of 1 over x squared y, all raised to the 9th power, simplifies to 1 over x squared y. And this matches our expected result, confirming that our solution is correct. Therefore, we verified that the expression the 9th root of x squared y cubed times the 9th root of x y to the 12th divided by the 9th root of x y to the 21st times the 9th root of x to the 20th y cubed is indeed equal to 1 over x squared y. This solution demonstrates important properties of exponents and roots, including combining like terms handling negative exponents, and using the property that the nth root of a value raised to the nth power gives us the original value. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. Nenomatica, where mathematics meets YouTube excellence.